quantum functions. So if we were to take a look at like, no, that doesn't make any sense. What's the sine of 405 degrees? That's better. I like that better. All right. Well, the sine of 405 degrees isn't on the chart, so I can't memorize that. But the sine of 405 degrees should mean something to you. Evan, what does it mean to you?
Sine of 45 degrees.
You're absolutely right. Okay, so Evan's saying 405 degrees is really one time around, and then an extra 45 degrees. So if you know that the sine of 405 is the same as sine of 45 degrees, and you've already memorized the sine of 45 degrees, you know immediately that it is... Okay, I was sort of, in my mind, my perfect teacher moment, I had like the whole class in unison saying, root 2 over 2. It's okay, maybe next time. Let's, I could get a little fancier and say, the cosine of negative 300 degrees. And if you're thinking sort of like what Evan was thinking, you know that negative 300 degrees isn't on your chart, but negative 300 degrees is the same as, Sam says, 60 degrees. So if you know that they're the same, if you know that, hey, going clockwise 300 degrees is the same as going counterclockwise 60 degrees, those angles are the same, and then you know, without giving it really any thought at all, that the cosine of 60 degrees is
1 over 2. Oh, God.
1 over 2. So, can you see how we can add layers that after you have the basics memorized, we can add little small layers that make the problem just another little step, okay? And I suppose throughout the next 2 weeks, that's going to be my job, to keep adding layers until you feel really comfortable and confident, such that you're going to look back at like today's quiz and be like, that is a piece of cake. I will know that without a doubt. All right. All right. So we good? I want to talk today about the sine and cosine function. And it should actually make perfect sense when you think about the tables that you memorized and the graph of what it's going to look like. If you actually take that table and start thinking about it, let's think about it in terms of radians, because we just talked about degrees for a little bit, so let's just switch our thinking a little bit to radians. So pi halves, pi, 3 pi halves, 2 pi. So let's take the sine function, sine of x or sine of theta. All right, what is the sine of 0? You tell me because you have it memorized. 0. So 0, 0 is a point on that graph. And actually, if you think about amphibians' travels around the water wheel, she starts right at ground level. And what does she start to do? Go up or go down? No, it does not. Anne always starts her travels at water level and goes up. Okay? She always does that. That's the definition of Anne on the water wheel. As a matter of fact, it is non-negotiable. As a matter of fact, every time we measure the unit circle, we start at the point 1, 0, which is at water level, and we go up. This is our path around the unit circle. Okay? So she starts there. Let's see. At pi sixths, which is probably right around here. How high up is she at pi sixths? It's 30 degrees, but she is how high up? Halfway up. So she actually does half of that travel upward in the first 30 degrees. So that's a pretty quick, rapid rise. And then at pi fourths, where is she? Root 2 over 2. I don't know what that is. What's that, 0.7 something? All right. At pi thirds, which is a little less than pi halves, she's at root 3 over 2. And then finally at pi halves, she's all the way up at 1. So can you see how this is and climb to the top, so to speak? Is that all right? And if we sort of mirror this, we know that she's going to do the same thing from pi halves to pi, except in reverse order. Right? She's going to go back down. So if we're asking about 2 pi thirds, that's going to be root 3 over 2. If we're asking about 3 pi fourths, that's going to be root 2 over 2. And if we're asking about 5 pi sixths, that's going to be 1/2. Okay? And then the only thing that changes about the table now is instead of above the water, she now starts her descent below the water. So it's going to look something like this. All right. This point and this point and this point have very special names. And right now that looks like the name would be zeros, but it's not. They could be called zeros, but they have another special name. What is that special name? Meaningless praise for remembering. Tom? No, it is. That's true. Not what I was looking for. So, nice job, Tom. There's your meaningless praise, but not exactly what I was looking for. It is where the graph intersects the midline. That's true. As a matter of fact, I think this is true, Tom. Wherever sinusoidal function and the midline meet, or cross, or intersect, that determines these very special points. No, because if I shifted everything up. Say again, Max? Yeah, awesome. Way to go, Max. There's your meaningless praise. Good job.
You need to start handing out stickers again.
All right, you're right. You're absolutely right. What are you talking about, crazy kid?
Oh, the box actually says reward stickers.
Yes. So those are called points of inflection, and something important happens there. Do you remember from like chapter 1 or chapter 2, what attribute of the function changes there? Mo?
Goes from concave down to concave up.
Perfect. All right, so whenever you change concavity, that's a point of inflection. And that's actually can be considered to be an important point. And I feel like, have I talked to you about hula hoops before? Maybe I have. Did I tell you about hula hoops? Okay, so if you're if you're making hula hoops, if that's your job, you know how hula hoops start, right? It's a fad. So it takes a little while to get. We have, right? It takes a little while to get going, but then it skyrockets. But then, as all fads do, they level off. There's only so many hula hoops people are going to buy.
Wait, why isn't that
Really? Are people going to continue to buying hula hoops?
I thought we had exponential graphs that leveled off.
No. What's that? That actually. What? Say again?
Nothing.
Oh, I thought you said something special.
No. But can we make it skip it?
Yes. Oh, with a little
I love this.
the lemon?
I was not very good.
Was it a lemon on it? No. Did it count how many times it went around? Okay. Back in the day, they used to be lemons. I don't know what it was called. It was called like the lemon thing, and it was basically like something, and it didn't count. Like I don't know what. So Evan, pogo sticks would be the same thing. This is important. This behaves at the beginning exponentially, but then levels off. This has a very special name, and it's called a logistics curve. Okay? An exponential curve just keeps going up. You also might, what did you call these in biology? S-curves, or is that what you call? Okay, so they had a special name. It's not just exponential. It's exponential with a twist at the end. Go ahead.
Can you give us a quiz with that graph?
It may have ended up on quizzes, tests, or mid-year exams. Okay.
The one Sam didn't tell anyone. Oh, yeah. Yep.
All right. Here's your sine function. We can tell a few things. Let's actually go and I'm going to graph it on my calculator. I'm going to go sine x, and you have to decide if you want to graph it in radians or degrees. I'm going to go to mode, and I'm in radians, and I'm going to stay in radians. Okay? So if I go to my window, a good window, if you're in radians, would probably be negative 2 pi, which is around 6.238 radians, to 2 pi. Now, that's what your x is going to be. So we're going to look at from negative 2 pi radians to 2 pi radians. What about the y values? What does this sine function oscillate between? 1 and negative 1. Okay? So if you wanted to, you could leave negative 3 and 3. I think I'm going to change it to negative 2 and 2. And if we take a look at that graph, there's a picture of 2 periods of the sine curve. Okay? And let's see. Let's clip it and talk about some things about this sine curve. All right. Period, amplitude, midline. Talk about those. All right. Who wants what? Pick one and tell me what you want to do. Peter, what do you got? Awesome. All right. And the amplitude is how high above or below the midline the function goes. So the amplitude here is 1. Okay? Danny? The midline is 0. That's right here. All right, so the midline is at y equals 0. Okay? And Danny, calling someone to give me the period here. Close, but not quite. It's a little less.
Isaac.
A little bit more.
Oh, wait.
So if it helps, what did we say we're measuring the degrees in? Degrees or radians?
Exactly.
All right, I'll tell you. We're measuring in radians. Okay.
Oh.
So if we're measuring in radians, you can actually tell me exactly how much that is to complete one cycle. How many radians to complete one full cycle? Think of your table if you need to. How far do we have to go to start repeating ourselves again? You want me to find? Yeah. That's exact. Say it loud and proud like you mean it. That wasn't that loud and proud, but yeah. Wherever you measure, if you measure from max to max or min to min, or the midline going up to the midline going up, remember, don't get fooled. Don't do midline to midline, because that would be only half the period. You have to do midline going up to midline going up. It's going to be 2 pi. It's the same as 360 degrees. And that's our basic sine function. Now we can alter a lot of that, right? If you want to, you could change the amplitude. And if you do insert a 2 in there, hey, check it out. The amplitude increased. It's a vertical stretch, right? Does this sound familiar? We talked about this like a couple days ago. Yeah? Okay. If you didn't want to change the amplitude, you could change the midline. Let's just add 1. It's a vertical shift, right? So the midline is now at y equals 1. Okay. All right. Let's start talking about changing the period and doing horizontal shifts. It's good. All right. Okay, so let's go back to this. Changing the period, what is that going to mean in terms of the function? What are we doing by changing the period? Elizabeth?
Changing how long it takes for the function to complete one full rotation.
Okay, so either it's going to take longer or shorter to do one full rotation than 2 pi. Let's, for example, do shorter. So the function might look like this. Whoops. I got a little messy at the end. All right, do you agree that has a period probably is twice as much Like it happens in half the time. So what attribute of the function, what are we doing? Vertical, horizontal, shift, stretch, compression. What is that? What did we just do to the function? Jennifer, what did we just do to it? I didn't take this and make it any bigger. So I'm not making it any taller. The function's actually the same. All right, I'll go with that. Like, so we're going to do, instead of, so it does look like, I can see what it looks like maybe we took this point and stretched it up, but we didn't change where any of the zeros were. Sorry, we did change where the zeros were. A vertical stretch would have kept the zeros where they were and stretched it out like this. Is that okay? Okay. Rafi says, I think horizontally we're just pushing it. We're making a compression. So this is going to have to remember about chapter 5. How do we do compressions? Where does that happen? Horizontal compressions. Where does that happen in this function? All right, it's in the parentheses and it's by the x. So that's exactly what we need to do. All right, so if you want to, Travis, if you want to make this happen twice as fast, which means we're going to compress it, remember it's a little counterintuitive. You need to insert a 2. And if you put a 2 there, it's not going to stretch it out twice. It's going to compress it. It's going to make it happen twice as fast. And if you look at that graph, sure enough, that happens twice as fast. All right, so there's your period. So you can change your period. And then the last thing we might want to talk about is shifting to the left or right. And here's what I'm going to do. I'm going to shift this, second, insert. I'm going to shift it to the right by pi halves. So I'm going to subtract, parentheses, pi over 2. Shh, Keith, up here. And if you take a look at that graph, do you see how we shifted everything over? Like it's a horizontal shift over? And actually, this is a great time to introduce our friend cosine. The cosine function is very similar to the sine function, except instead of starting at 0 and going up, the cosine function starts at 1 and drops down. And if you remember your table, that's exactly what it does. And here's what I want to actually convince you of. We actually don't need sine and cosine. They're redundant. You could actually get rid of one of the functions and you'd be totally fine. Do you believe me? Not really. What could I do to the cosine function to actually get the sine function? Like what? All right, if we took a negative, insert negative. Does that give us our sine function? Not quite. Sine has to start at 0 and go up. So flipping it was a good thought. Flipping it didn't work, though. Second thought. So you want to do minus. You want to shift it over. All right, Max. Is that we're going to say shift it over? You want to hold on and see if this works, and if it works, we're good. If not, we'll call you, Max. Let's see. Shifting it over. Huh. That looks exactly like the sine function, I guess. Isn't that what the sine function does? So look, sine and cosine are the exact same function, except they're just shifted over. Okay? The sine function is cosine shifted over to the right pi halves. All right. You want to ask some questions? Can I ask you some questions? What do you want to do? Evan?
So will we be able to find those angles, like on that sheet or whatever, that we use?
Say that again? Are you sure? I just don't know what the question is. I'm happy to answer.
That's backwards.
Okay. Anything else? I'm going to ask you questions if you don't ask me. Tom, question? You sure? All right. Let's take a look. Wow, look at all those questions we haven't done. All right, let's take a look at 24. And here we have a bunch of functions, sine and cosines, and we're doing a little something, altering them just a little bit, and we're going to try to match them. This is a without a calculator exercise. Okay? So, calculator's away, and if you think you see a match, raise your hand and let me know, and I'll call on you, and then you can call on the next person. Travis, do you think you see a match? All right, Travis is going to link up A with 2. I think so, right? Because that's just the sine function that you recognize almost immediately now. That's good, Travis. Call on someone. 3 is going to match with C. What does C do to the sine function? It shifts it up 1. Is that exactly what 3 did? It is. Shifted it up 1. Good, Danny. Call on someone. It's not Jeopardy. Just tell me. You guys are all asking me. Say, 4 is B. Yeah. Let's see. 4 is going to be our cosine function. All right. Is that what cosine looks like? Starts at 0, 0. Say no. Say no. Say no. Yeah, good. No. Try again, Pete. Cosine is definitely 1. Okay, B matches up with 1 because cosine starts at its maximum and goes down from its maximum like that. Sine starts at the midline and goes up. All right, call on someone. Oh, I think we did something wrong, but that's okay. I'll let you tell me. All right, call on someone, Pete. 5 and D. What does 5 do to the cosine function? It definitely does. And that's exactly what 5 does. I agree. I'm going to say something else. I do think we did something wrong, but that's okay. I'm going to let you tell me. Monty, call on someone.
Is F 6?
F is 6. F is 2/3 cosine x. What would 2/3 do to the cosine function? What would that 2/3 do? How? Oh, that's backwards. Shoot. It would. I made a mistake. I can see it now. Okay. This is my fault, and I'm sorry. I'm going to change it on mine. It's not going to change it on yours. This should be 3/2. And this should be 3/2 instead of 2/3. I got those fractions totally backward on the sheet. All right? And I don't like that. Yes, Evan. Yes, you can. So, Travis, F is going to do what to the cosine function? No. You said stretch it. That's what you said. So say it again. Stretch it vertically. I agree. So F is going to match with 6. It leads us to an interesting observation, though. Call on someone, Travis.
Well, I was just going to say that I think that A is 4 and not 2.
You're absolutely right. Tell me why.
Because
what's the difference between 4 and 2? They look exactly the same to me.
2 is more stretched out vertically.
Yeah.
Like compared to the other ones. 3.
And what should 2 match with then? Say it loud and proud.
E.
E. Okay. Do you see the difference between A and E? It's a very subtle vertical stretch, and actually the typo from E and F makes that a hard question to answer because it looks like it was 2/3 and it should have been 3/2. So I apologize. Do you want to ask any questions on that so I'm sure that I didn't thoroughly confuse you, or is that something that as long as we said the mistake, you're okay understanding it. Does anyone not understand the mistake I made? Evan?
I have a question.
Okay.
I feel like D and F are like they're flip and
So here's the difference between D and F, and it's a subtle one, and students sometimes make this mistake. D has a midline at 1. Hold on. And F, Evan, has a midline at 0. And so that midline's a big difference.
I was just thinking like comparison to the other graph. Like, I feel like there's two things that are it's upside down and
All right. Have a great Monday. It's not upside down, it's the cosine graph. Cosine starts at its maximum. So there's a difference between cosine and sine. Oh, is that okay?
So wait, so is the difference in sine? I'm not watching this. This is a really good start.
It was a good game.
Cosine starts at its maximum. Sine starts at the midline. Not its minimum, at the midline, and it goes up. Okay?
Half of the last quarter.
You mean the last 8?
And so
I could say half of the last inning.
no, you joking.